Hi, so welcome to MathStat 341, probability. This is lecture 25. And what we're going to do today is we're going to continue with generating functions, moment generating functions, and the like. And so what I want to do today is talk a little bit about the differences between generating functions, moment generating functions, characteristic functions. They're all closely related to each other. And it all comes down to trying to find the right path through the algebra. And that's not surprisingly the theme for today. It's the theme for a huge amount of this course. It is so easy to follow proofs line by line by line when someone gives you the argument. It's how do you come up with the approach to get there on your own. And a lot of it is trying to figure out which object is going to be the easiest to study. And so, for example, if you remember the proof of the fundamental theorem of calculus, and I know this question assumes that you've seen at some point in your life, proof of the fundamental theorem of calculus, at one point you have a telescoping sum. So if I give you, 13 minus 1 plus 17 minus 13 plus 88 minus 17 plus 1701 minus 88 plus 24601 minus 1701, what does the sum equal? Yes, Jean Valjean's neighbor. 24600. Okay. How did we get that so quickly? Well, we noticed that we have diagonal cancellation. And so rather than summing it horizontally, if we just notice that we have all this cancellation, the sum becomes much easier to study. And by rearranging the algebra like this, it becomes trivial. If we try to do it the long way, it's unpleasant. And that's what I want to do today. Is I want to try to emphasize what is the right thing to look at. So last time we started by looking at the generating function, and given some sequence of numbers an, we define the generating function as this power sum. It's the sum of an s to the n for all s where this converges. There is one value of s where it's not a big deal to establish convergence. What value of s is that? At 0. So when s equals 0, it's going to converge. Will it converge for any other s? And it turns out it's very useful if this converges in a neighborhood of 0. If that converges for some s that's a little bit positive and some s that's a little bit negative. Unfortunately, we don't always have that. The generating function does not always exist in a neighborhood of the origin, and that's going to cause some trouble. Fortunately, it has cousins that do exist. All right, so the first big result is the uniqueness of generating functions of sequences. And this is something that you would hope would be true. If I give you two different generating functions, they should be unique. Now, as a warning, before we do this, one of my favorite functions in all of mathematics is the function f of x is e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. All of its Taylor coefficients, all of its derivatives at the origin are 0. So if you try to find the Taylor series is identically 0. But f is not identically 0. What this tells you is that Taylor series are not unique. The Taylor series for sine of x and 1701 f of x plus sine of x, they have the same Taylor series. That sucks, right? You would hope that if I know the Taylor series, I know the function, especially if the Taylor series converges for all values of x. Well, here's a situation where the Taylor series converges for all values of x. And it could be sine of x, could be 1701 f of x plus sine of x. It could be so many different things. Why is this problematic for us in probability? Well, instead of Taylor series, what we're going to have is moments. And the hope is that if we know the moments of a probability distribution, that uniquely determines the probability distribution. Turns out that is false. The moments do not uniquely determine. You need more than just the integer moments. You need technically a sequence of moments that accumulate. So for instance, imagine we knew the moments at 2 plus 1 over n for any n. So that would be a sequence of moments accumulating at 2 at the second moment. If we knew that, then using some results from complex analysis, we could then get a unique probability distribution. This is one of the many reasons why I love teaching probability and complex analysis in the same semester. And if people are interested, it's about 2 lectures. And I'm happy to just do that, privately and just talk to anybody who's interested about how do you actually prove stuff like this rigorously? What are the tools that we need? Why the hell do we have to detour into complex analysis to prove stuff about real value distribution? But this just shows you how careful we have to be in the subject and what is needed. Fortunately, things are very nice if I give you just a sequence bless you of numbers. So if AN and BN are 2 sequences of numbers with generating functions GA and GB, which converge for, say, the absolute value of S less than delta, then we're in really good shape. It turns out that the 2 sequences are equal if and only if the generating functions are equal. And we can recover the sequence terms by differentiating the generating function. One of the 2 directions is trivial. Which direction is trivial? Yeah, if AI equals BI for all I, then clearly the generating functions are the same. There's really no content in that direction. That is a no shit, right? The other direction, that's the real content. If the generating functions are the same, then that means that the functions themselves have to be the same. And one way we could do this is we could do it term by term. So GA of S is A0 plus the sum and goes from 1 to infinity of AN Sn, and that equals B0 plus the sum and goes from 1 to infinity of Bn S to the n. What can we deduce from this? So what must be true? What's a good value of S to take? This relation holds for all values of S. One value of S is screaming, please use me. What value of S should we try? 1 is a reasonable try, but we don't know that it converges at 1. There's only one value, you want to correct it. There's only one value we know where it converges. 0. So if we take S equals 0, what does the left-hand side become? A0. What does the right-hand side become? So if we take S equals 0, that yields A0 equals B0. And then we get S times the sum and goes from 1 to infinity of AN S to the n minus 1 equals S, the sum n goes from 1 to infinity of Bn S to the n minus 1. What can we do to both sides? So I now have this relation. I have S times this sum equals S times that sum. And this holds for all S less than some delta. So what could I do to both sides? Yeah, I can remove the S. So remove S. Yeah, and then we would just get A1 equals the sum and goes from 2 to infinity of AN S to the n minus 2, I'm sorry, S minus 1 equals, I'm sorry, and this is, that's plus. I'll just really emphasize that it's plus. Equals B1, and now I have to really emphasize it here as well, which is annoying, but then the sum n goes from 2 to infinity of Bn S to the n minus 1. And now what do we take? Take S equals, take S equals 0. Yep, and that implies that A1 equals B1, and now we do shampoo mathematics. Lather, rinse, repeat, just keep doing this again and again and again, and we can just read it off term by term by term. In some sense, what's really going on is we look at GA of S minus A0 over S equals GB of S minus B0 over S. Really, that's what's going on in the background. I'm not going to prove the result that you can recover by differentiating. You can just see that, well, if I have a series expansion, if I differentiate it n times, I would get an n factorial, and the only term that would then survive when S equals 0 is the following. So this would be AN equals this, evaluated at S equals 0. Right? Any questions about this result? So this is a nice result that if I have a generating function coming from a sequence equal to another generating function coming from a sequence, the only way that can happen is if they are the same sequence. Excellent. All right, so the next is convolution of sequences. We've seen convolution before for functions, and this is the discrete version. And so we say we have two sequences, AM and BM. We define their convolution as CK is A0 BK plus A1 BK minus 1 all the way to AK B0. Or equivalently, this is just the sum of AL B to the K minus L. L goes from 0 to infinity. And to think about this, if we have, say, the sum of A L x to the L, L goes from 0 to infinity, times the sum, M goes from 0 to infinity of Bm x to the M. Do you agree that this is going to be a sum K goes from 0 to infinity of CK, which will be a function of the A and the B times x to the K? There's just going to be some polynomial. And how do I get a term of various things? Well, if I want x to the 0, it's going to be A0 x to the 0 times B0 x to the 0. That's the only way I can get an x to the 0 term. And so that tells me that C0 is A0 B0. If I want to get an x to the first power, I could have A0 x to the 0 times B1 x to the 1, or I could have A1 x to the 1 times B0 x to the 0. That gives me C1 is A0 B1 plus A1 B0. Right? And you can see that this process just continues. Again, it's shampoo mathematics. As we continue down like this, if we look at what's going on here, if I want to get a term x to the k, if I have no x's from the first, I have to have k from the second. If I have one x from the first, I have to have k minus 1 from the second. So what this is telling us is if we take the product of two sequences, the product of the two sequences is going to be a new sequence, and it's going to be arising from the convolution. Oh, so this is probably going to tell us that generating functions behave nicely under products. Again, I probably should have, put the image back from when we did sums of uniform random variables, and we saw just what a monster it was to look at the density of 4 uniforms added together. And doing 8 would be even worse, but it's approximately a normal. And so the idea is rather than working with these painful exact formulas, we want to try to work with approximations. Does anybody else hear the music? Yeah. Okay. Do you hear ABBA or do you hear something else? Not something. Yeah, I always hear ABBA. Okay. So when you are looking at this, this is screaming at you so loud that the music is drowned out, that there should be a nice result about products of generating functions. If I take the generating function of A and multiply it by the generating function of B, that's going to be the generating function of the convolution. And in fact, that is exactly what comes next. That's the big lemma. So G of A is the generating function of the sequence A, G of B the generating function of the sequence B. And then if we look at the sequence C as A star B, that's just the generating function of A times the generating function of B. The whole idea is multiplying two infinite sums is bad. Multiplying, just taking one and if A and B are the same, just taking it to a power, this isn't so bad. So the whole idea is to try to find a good handle on stuff like this. And of course, what if we had A star B star C? What would the generating function of A times the generating function of B times the generating function of C equal? Yeah, the generating function of A star B star C of S. And this is done by grouping. it's A star B star C.
The convolution. Yeah, I guess it is.
So you can prove that it's associative by just going like this and just expanding things out. So again, it's just filling in the algebra, but it is amazing how powerful grouping things is in mathematics. So whenever you're in doubt, if you can prove things for two, you can keep grouping. Did we do the proof by induction that everybody has the same name in this class? Okay. If there's time at the end of the class today, I will prove that everybody has the same name. Okay. And again, it's a nice proof by grouping. So you have to be careful. Sometimes grouping fails. So you do need to justify and make sure everything is fine. But we know in this case, it's true. So in this case, we get the generating function of A star B star C of S is the generating function of A star B of S generating function of C of S. Because we just have two sequences. And now we use the generating function of A star B as the generating function of A times the generating function of B times the generating function of C. So in fact, any finite convolution, we're going to have the result. So even though we only stated it for two, two is the hard case. So we're really doing a proof by induction. How many people have never seen proofs by induction? Okay, good. So the base case is trivial. That's just saying if C equals A, then G of C equals G of A. Although fortunately we did prove that earlier. The real meat is the proof when you have C as A star B, that the generating function of the convolution is the product of the generating functions. Okay, so continuing, let's see how we can use this for various things. Is this written large enough that it's readable? Okay. It's always a balance of trying to give myself as much space as possible while keeping things displayed. So again, I'm defining CK, or I guess here CN, to be the sum of AL, A to the N minus L. So I'm convolving a sequence with itself. What sequence? I'm actually choosing AL to be N choose L. And we are letting C be A star A. Okay. And so we know that the generating function of C is the generating function of A times the generating function of A. This allows us to prove a beautiful result. The sum of N choose L, N choose N minus L. Well, N choose N minus L, why is that the same as N choose L? So why? Yeah. Yes, if you look at the algebra, they're the same. The other thing is, if you choose L people to get something special, and only those L people get something special, that's the same as choosing exactly N minus L people to exclude. But it sometimes sounds better. As you get older, you will start having medical problems almost surely. Would you rather hear that there's a 95% survival rate or a 5% mortality rate? Yeah, I mean, either is the correct answer. But for a lot of people, do you think they would rather have the focus being on how many survive or the focus on how many die and how many survive? It might be interesting to look at how COVID information is presented. All right, so when we're looking at this, we have a product of binomial coefficients. Well, that's just A star A. And so by definition, that's just going to be Cn. So if we can just figure out what the nth term is, we now have a formula for the sum of N choose L squared. And so what is the generating function? So the generating function of A of S is the sum L goes from 0 to N of N choose L, S to the L. I'm going to write it as 1 to the N minus L. So that's just by the binomial theorem. It's just 1 plus S to the N. So I'm just taking my sequence to be N choose L. N is fixed. Okay. Is everybody comfortable with this for my generating function of A? Well, the generating function of C of S is just the generating function of A times the generating function of A, which is 1 plus S to the N times 1 plus S to the N, which is 1 plus S to the 2N. But 1 plus S to the 2N is just the sum. K goes from 0 to 2N of 2N choose K, S to the K, 1 to the 2N minus K. If we take K equals N, we get the coefficient of Sn is just 2N choose N. And thus, our sum is equal to 2N choose N. So we've proved that the sum of N choose L squared, L goes from 0 to N, which is the same as the sum, L goes from 0 to N of N choose L, N choose N minus L, is just 2N choose N. So it's nice to see another application of generating functions. We can use these to prove identities. We could have proven this by story. And the proof by story is the following. So there's so many ways of doing this. They often do it with people getting together for dancing, people getting together for watching a sporting event. Let's do sporting event. We have N students from Williams. And then anybody, that's of course a perfect school, at least if you look at it in terms of football. And you want to give me an example of an inferior school, at least in terms of football. Amherst, yes. We even have a recent data point on that. We'll have N students from Amherst. And so we could ask, how many ways can we form a group of N people? So there's 2N choose N ways to form a group of N people. And it's the same as I could choose N from Williams. It's just N. So I choose L from Williams. And then we would have to choose N minus L from Amherst. So I love proof by story, but proof by story is a very hard thing to do. You have to see the right way to look at it. It's always nice when there's multiple ways of proving something. So we could prove this by generating functions. We could prove it by story. A lot of combinatorial identities are proven by story. Any questions so far? If we have time later today and prove that everybody has the same name, we will of course prove as a corollary that all colleges have the same name. All right. So the next one is probability generating functions. So all we're doing is we're taking the phrase generating function, which we've looked at before, and we're shoving the word probability. So what is this doing? It's just telling us what we're choosing the ANs to be. We're choosing the ANs to be related to something from probability. So let's let X be a discrete random variable taking on values in the integers. So it's extremely important that we decide what we are talking about in terms of where the probabilities live. So these are discrete random variables, continuous random variables we will talk about later. And we are assuming that things are integer. Can somebody give me an example of a random variable that only takes on integer values? Let's say non-negative integer values. Coin toss. Give me another example. That's only like 2 values, 0 and 1. Number of popcorn buckets sold. Rolling the die. Something related to sports. Yeah, number of points scored in a game. No matter how bad some teams are, they're not going to score a negative number. And no one is going to score half a point, at least in the standard sports. In some other sports, you can potentially get half a point for something. But in the standard sport, your score, the number of runs, is going to be an integer. So there's a lot of things that are given by integers. On a sadder note, we could have the number of collisions at an intersection, the number of accidents, number of patients who die. Or on a happy note, number of days without an accident. If you ever watch The Simpsons, they have some nice little, how many days it's been since an accident at the nuclear power plant. So there's a lot of things in the real world that do take on integer values. So this is not an unreasonable restriction to look at something like this. So we say g of x is the generating function with our sequence, with am is the probability that x equals m. So we are allowing negative values to be assumed as well. For most of the applications, we will only be dealing with positive values. On what basket does bird beat magic? It's not going to be on the negative third toss. If x is only non-zero at the integers, a very useful way of writing the generating function is to know that the generating function of x is just the expected value of s to the x, where x is our random variable. What does that mean? Well, it means it's the value s to the x. So x ranges over the integers, so it will be s to the m times the probability that x equals m. This is how we calculate probabilities. This is how we calculate expected values. So the generating function is really just the expected value of s raised to the random variable. So more generally, if the probabilities are non-zero at most accountable set, instead of having s to the m, it would just be s to the x sub m, and then the probability that x equals m. So the question then becomes, can we compute this for things that are nice? So somebody give me a reasonable probability distribution that is integer valued. So uniform is going to be too easy because it's only going to take on finitely many values. So give me a little bit of a challenge. Let's have it have infinitely many values. So natural ones are geometric, Poisson. So we've done Poisson already. We can do Poisson again. So for Poisson, the probability that x equals m, so we'll say it's Poisson with parameter lambda, would be lambda to the m, e to the minus lambda over m factorial. So we would want to calculate the expected value of s to the x. That would be the sum, and goes from 0 to infinity, s to the m, and then the probability would be lambda to the m, e to the minus lambda over m factorial. Well, we pull out e to the minus lambda, and we have the sum, m goes from 0 to infinity, of lambda s to the m over m factorial, e to the minus lambda, e to the lambda s. So it equals e to the negative lambda 1 minus s, or e to the lambda s minus 1. So what values does this converge? So does this sum, yeah, this sum makes sense because we have m factorial that grows so rapidly that it doesn't matter what s is. S to the m is only polynomial growth, m factorial is more than exponential decay. And this is converges for all s. Even complex valued s if you want. So we've done the Poisson random variable before, but this should hopefully give you an idea of why I love the Poisson random variable so much. Its generating function exists for all s. When you are studying objects, it's really nice if they exist. You should take the time and try to get a sense of, so what are examples of this set? They tell the story of a graduate student who proved a result about a space of functions that have certain properties. And then a few years after the person got their PhD, according to the story, somebody proved that these properties imply that every function in the space is constant. And these results were already well known for constant functions. Constant functions are differentiable, constant functions are infinitely differentiable, constant functions are given by the Taylor series. It's really not that big of a deal to prove these results about constant functions. but the properties were given in such a way that it was not initially clear that this was the space of constant functions. When Kepler was studying the orbits of planets, he had great data from Tycho Brahe, and he was looking at the orbit of Mars. Does anybody know what's really interesting about the orbit of Mars as seen from Earth? I believe it has that retrograde motion where at some point in the orbit, it looks like it stops and then goes backwards and then goes forward again because of the way Earth and Mars are moving around the sun. And he was trying to understand the orbit of Mars. And at one point, he actually wrote down an equation for the orbit of Mars, but was disappointed because he thought it was going to be an elliptical orbit, and he had something else. And he didn't realize that what he had was an alternate definition of an ellipse. And he actually had the elliptical orbit, but didn't recognize it as such. So really finding ways to work through the algebra is essential. Having examples that we can play with is great. The Poisson is a great example to play with. Did I bring my portable Cauchy distribution to this class yet? Oh, I thought I had. All right, I will try to remember. A couple of years ago, a student actually gave me a Cauchy distribution. Truncated, of course, because the Cauchy distribution is tough to fit. Cauchy distribution is a great distribution to play with because it's a probability distribution, but what is potentially bad about it? So what's challenging about the Cauchy distribution? Yeah, so you can argue as to whether or not it has a mean of 0. It technically doesn't, but it's at least symmetric about the origin, so I can see the argument. It's wrong, but I can see the argument. It definitely does not have finite variance. So when you're trying to test and see how good are your results, if you only need to assume it's a probability distribution, shove in the Cauchy and see what happens. The Cauchy distribution is also an example of a stable distribution. Cauchy plus Cauchy is a new Cauchy distribution, just rescaled a little bit. So you have some beautiful results to simplify the sums. Okay, the next is an absolute non-shocker. Let x1 through xn be independent random variables, discrete, taking on non-negative integer values with corresponding probability generating functions gx1 through gxn, then the generating function of the sum is the sum of the generating functions. Why is this true? If you're thinking about a proof, you're making it too hard. Oops. So what's the answer? Okay, so one thing is you could do this as the expected value of s to the x1 plus xn. And then this is just the expected value of sx1 dot 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 sxn. Because they're independent, it's factors. And then this is just the generating function of x1 to the generating function of n. But there's another proof. Okay. Sorry? Yeah, if you go back a couple of slides, we proved that if you have a generating function, the generating function of the convolution is the product of the generating functions, right? That's just applied right here. But adding is convolution. Shorter proof. Adding is convolving. Use lemma 19.4.2. So it's fine to prove it directly. But again, the probability generating function is just a generating function where the sequence is coming from a probability distribution. So any results we have for generating functions have to hold for probability generating functions. Right? So again, it's not bad to prove it directly. but it's nice to just know we've already got the proof. Okay. So the density of a sum of independent random variables is the convolution of their probabilities. We've done this before, right? This is just review. Review did this before. Since we study sums all the time, shows the value of convolutions, right? We want to get our hand on the density of a sum. Well, the density of a sum is related to the convolution. So any process we have, which is nice with respect to convolution, is almost surely worth studying. So because the generating function of a convolution is the product of the generating functions, it suggests the generating function might be the right thing to study. It isn't, but it suggests that it's a good thing to try. And if it doesn't work, maybe if we modify it a little bit, we will find something that works. Okay. So the next is the probability generating function. If we have a continuous random variable with density f, then the generating function of x is just the integral of s to the x f of x dx. And this will be true for whichever values of s this exists. Is this really a surprise definition? No. This is basically, replace, sum with integral. And again, we would have the generating function would just be the expected value of s to the x. Now, one of the problems is we do not have all these uniqueness results in the case when we have a generating function coming from a continuous setting. And so, again, here, we're not defining it as a sum. So what we're saying is really the good way to define generating function is through the expected value. So maybe the correct general definition of a generating function is through expectation. Because this makes sense if it's both an integral or a sum. And again, if we think about the generating function initially defined for a sequence, if we do it for a discrete random variable that's supported on the non-negative, that's supported on the integers, everything makes sense. That generalizes nicely like this. So let's define our generating function to just be this. And then not surprisingly, you can prove similar results will be true here. What do you think a generating function of a sum would be if they're independent? The product. And so we're just putting everything down explicitly. If we have two densities, F1 and F2, we've talked about this before, the convolution is just the density of the sum. So, again, if xi has density fi, then x1 plus x2 has density f1 star f2, at least if independent. And it turns out that this will always exist. So we have a way to write down the density of a sum. And then the non-shocking result is your sum of continuous random variables. The probability density function of the sum of independent random variables is the convolution of the product density functions. In particular, if x1 through xn have densities f1 through fn, then the density of the sum is the convolution of the densities. We only proved this in the case of 2. How do we prove it in general? Grouping. So proved when n equals 2, general case by grouping. And then it turns out that convolution is commutative. A star B is B star A, F1 star F2 is F2 star F1. Technically, the simple proof only holds when these come from probability distributions. Because when they come from probability distributions, then F1 star F2 is the density of the random variable x1 plus x2, which of course is the same as the density of x2 plus x1, because addition is commutative. In the general case, when these distributions are not probability distributions, you have to then go back to the definition, and you have to do a little bit of work. So it's trivial if F1 and F2 are densities as have an interpretation through x1 plus x2, which is the same as x2 plus x1. In general, do some algebra or calculus. In general, you have to just prove it. But if we're in the fortunate case, now, which class is this again? Not real analysis, also known as not complex analysis. I know I sometimes have to be reminded, but I think I heard somebody say probability. So given that this is a probability class, it should not come as a surprise that we're only going to really be using this when F1 and F2 are probabilities. So the simple proof is enough for us, but it's good to know that you can generalize it without too much trouble. Okay, so now definition of moments, we've seen this before. So X is a random variable with density F, standard notation. Its kth moment, we denote it as mu k prime, is defined as the sum of xm to the k f of xm, where it is a discrete random variable taking on the values xm. If it's continuous, it would be xk f of xk. Of course, I could allow it to take on negative values as well. It just depends what I want to study. Now, as soon as you see a prime, you should be asking, why do we have a prime in the definition? That probably means this is not the quantity we want to study. And so the quantity we often want to study is not the moment, but the centered moment. And so we define the kth centered moment as the expected value of x minus the first moment to the kth power. Now, we have, let's see, what would be the first centered moment? First centered moment would be 0. So note, mu1 is just 0, mu1 prime is just the mean. And so what we're basically saying is, let's just adjust our distribution to have mean 0. And then we're just calculating things from this. Okay? So the kth moment is just the expected value of x to the k. Any questions on the definitions? So again, when we're trying to deal with sums, it's often nice to standardize or normalize. And if I adjust things to have mean 0, as I add more and more copies, well, I know I'm still going to be centered at the origin. I'll be spreading out, so I might want to then rescale so that the resulting sum has a standard deviation of 1. Okay. Any questions on the moments? Do we all agree that moments are useful? And again, the prayer, the hope is that if you know the moments, you know the distribution. Yeah, I mean, you would just extend the sum to go from minus infinity to infinity. Yeah. It's just most of the distributions we look at, the discreteness is on the non-negative integers. And so I just isolated that, but you could, of course, allow yourself to go in both directions. Okay. So the last thing I think for today is the moment generating function. What do you think the moment generating function gives you? Moments, right? Every now and then something is named well. This is very different than cosecant and secant alliance. The moment generating function gives you the moments. So the moment generating function is defined as follows. So x is a random variable with density f. Its moment generating function is denoted m. So when we did generating functions, we denoted with a g. Moment generating function, we denoted with an m, is defined as the sum of e to the tx f of xm, or the integral of e to the tx. So we can really view this as it is the expected value of what? e to the tx. And the generating function of x at s was just the expected value of s to the m. The moment generating function was the expected value of e to the tx. Oops, that should not be m. That should be so it tells you, hey, there's a really nice correspondence between generating functions and moment generating functions. Basically, s goes to e to the t. It's a simple change of variable. It's not a big deal, right? And so essentially any result I have for generating functions, I can move to moment generating functions by just saying, well, look, the moment generating function is just the generating function evaluated at s, where s is e to the t. So I can convert from one to the other, or I can just prove things directly. Let's take a quick look at to why this has its name. So the moment generating function x of t is the expected value of e to the tx. It's going to be the integral from minus infinity to infinity of e to the tx f of x dx. And then since we're short on time, I'm going to just write e to the tx as a sum n goes from 0 to infinity of tx over t to the n x to the n over n factorial f of x dx. I'm just expanding the exponential. Okay, I'm not going to worry about justifying do things converge because we don't have much time. So clearly I can just interchange the sum and the integral. I'll pull out an x to the n over, oh, sorry. I'll pull out a t to the n over n factorial. And then I have an integral from minus infinity to infinity of x to the n f of x dx. It converges. If the integral of the sum is the sum of the integral. Well, what is the integral of x to the n f of x? If f is a probability distribution, what is this integral equal to? The nth moment. So this is then just going to be the sum, n goes from 0 to infinity, of the nth moment over n factorial times t to the n. And this is why it's called the moment generating function. When you look at its Taylor series expansion, the Taylor series expansion of the moment generating function gives you the moments. So what this means is, imagine I give you a probability distribution and you can calculate the moment generating function in closed form. Beautiful. If we can then expand it out, we then get first moment, second moment, third moment. Or I could just take derivatives and get first moment, second moment, third moment. So the moment generating function, not surprisingly, is going to be extremely useful. The difficulty is that it's not always going to exist. Can somebody give me a random variable where the moment generating function will not exist? Yeah, when in doubt, if you're asked for something not to exist, go with the Cauchy distribution. Why? Well, you can argue whether or not the first moment exists. By the time you get to the second moment, it's infinite. So when we try to calculate the moment generating function of the Cauchy, it completely blows up. So I'm going to just state the following, we may go into more detail about this tomorrow. But if I give you a random variable with moments mu k, the moment generating function is what we just showed is, if you look at the Taylor series expansion, is the following. If alpha and beta are constants, the moment generating function of alpha x plus beta is e to the beta t moment generating function x at alpha t. I strongly urge you to try to prove this yourself. If you get stuck, look at the book. If we have two independent random variables, the moment generating function, the sum is the product of the moment generating functions, and more generally, the moment generating function of a sum of n independent random variables is the product. And if the random variables are all the same, you just get something to the nth power. All right, so I finished it in exactly 50 minutes. There was a lot of material today. I strongly urge you to try to do some of the algebra on your own. It's in the book. We'll do some more on Wednesday. All right, have a good day.